This is a LabVIEW Beginner Lesson Series where we make a heart rate monitor. This is the first lesson of Lesson 3, Architecture and Compartmentalization. In Lesson 3, we will not focus on improving the heart rate monitor, we will focus on the architecture. This means that we will focus on separating and cleaning up the code so that it's easy to add modularity and functionality later, which we will do in Lesson 4. Having a good architecture is important because it makes it easier to fix code, maintain it, or add code later. This is lesson 3-1, separating out the hardware code. The focus of this lesson is to separate the hardware acquisition to its own loop. This is important because other parts of the application which is not relevant to the acquisition might halt the acquisition. To do this, we need to set up communication from the parallel hardware acquisition loop to the other loop. We will do this with something called a user event, and we'll also use a local variable. We'll start by setting up the folder system properly from the start, and now we'll not base it on lesson, but rather functionality. So we'll just explore here, so you get to the right place, and here we're lesson 1, 2, but now instead we want to make a folder called launcher, because the main application launches the application. So we'll copy this because this is what we'll base it on. And here we'll call it lesson 3 because we'll use it for the whole lesson. And we can just call it launcher. We'll also make a virtual folder for this. You can now make the icon for this so it makes more sense. Heart rate monitor. Lesson 3. Launch. We can't fit launcher, so we'll just write launch. The goal is really to separate this out to its own loop and set up communication between this and this, so they run in parallel. The first thing we could do is just to move this in this corner. And we can also shorten this one by Control Alt, there you go, and there. So we'll need 2 loops. And we'll start with a while loop because we want them running continuously, so we'll still use a while loop. Inside the while loop, we want a case structure. This case structure will just shut down this loop if there is an error. The point of this is because when you have multiple loops and there is an error in one of them, it is good practice that they just shut down and not do anything, because this will alert you that something is wrong. And we'll hook up the error. You can just create a control from this one, call it error in. And we'll let this one run like this, and we'll add a shift register to it. Select there. This will loop the data, and you will soon see why this is nice. When this is running, if there is an error in any of the main code here, it will automatically go into this loop. And in here, we can just have a boolean that's true that goes here. And in the other one, we'll have the controller, but I'll move it over soon. The point is that if there ever is an error, it will stop. You could make this part more advanced to not stop at certain errors, etc. But the point is, it's good practice when you start making an application to stop at all errors, so you can figure out how your application works and which error you will encounter. Later, when you understand the error, you can make exception for it. But starting by making exception or not stopping on errors can cause harm to some product. So with our application, is so simple, there's really nothing that can be harmed, But say you were running a heating element or something, and rather than stopping the application when it's overheating, it just continues heating or something similar like this. By finishing and stopping the application into a safe mode when you're done, rather than just pushing through the errors, will reduce the amount of harm you can do. Again, this is not anything that we have to worry about for our application, but it's good practice. So it's better just to do it on every project that's larger than a few VIs. We will need 2 of this loop. We'll need one for this part and one for the acquisition part. What we'll do is just to copy this part. Control C, Control V, and just have it here. And then I'll press Control B to remove the error. And just like above, we want this one on the outside, we want this at the end, and we want this in the middle. And then we can hook it up, just mark everything, hold Control, and while holding Control, press space first and then W, and they will auto hook up. And we can add shift registers. We also need to connect it on the backside. So now we have dragged this one out of there and put it in its own loop. But still, there's no way to communicate it up. But before we set up that, let's just copy this part out. We also need to remember to take the timing in here. And then we will copy this too. But to avoid that we get a 2 after every indicator and control, we cut it rather than copy it. So hold Control, then press X, and then Control V. We then want to change to the non-error loop because we want this to happen when there is no error. And we'll just drag it in here. We can connect up the stop to this one. And let's connect up the error wires. We see that only this function or VI has an error going in and out. So we'll hook up that one. If we don't hook up the error wire from this, we'll get an annoying pop-up every time there's an error with a VI, and it will just continue coming up because we continue to run the application, and then we would need to stop it with abort execution. This means that something is bad because when the end user is using your application or you have compiled it, you don't have these same functions. You need to rely on the stop button, or it's stopping by itself, and it will do this now. If there's ever an error here, it will go in here, the shift register will take it there. Instead of choosing the non-error case, it will go to the error case where it will stop. There we go. We also need a shift register for this waveform. It's important to have a constant on the input of a shift register, or else it will take the last input it had, so from the last time it ran. You could want it for certain application, but then there's probably better ways of storing the data. But for this one, I want to start clean every time I start the application, and therefore I have an empty constant. We have now transferred everything from this original loop to these loops, so we can just delete this one. I made a mistake by connecting this one in here because this is where the raw data should go in, while this is where the raw collected data should go in. This is because I did the mistake earlier, and having the in and out at different location, making me think that it should go in there if it goes out there. So what we'll start by doing is actually move this one, disconnect the terminal, take it there, and then rename it to raw collected data out. And then we'll also move it just to indicate this. So now it will be much more obvious for you later, because I'd already forgotten and connected this wrong. What we also need, which there's no error for, is an input here. What we can do is say that this connection is required because, frankly it is, because this VI without the new data input is useless. So we'll add this. Now, by saying that this is required, it also complains about this one and cannot run before we have an input there. This is good because then it will tell you what you're missing when you try to run an application, and it will save you time in debugging. What we need now is for the data in this wire to go up here. It might look like you could just do this. They are wired together, this will send data up here, but what will actually happen now is that this loop will start, and this loop, it will wait until this one has stopped, and then the data from this one, the last data, will be sent up here. It will not work as intended. It will just first do acquisition for as long as you want, and then do one or work with the same data set over and over again. We also want the application to stop when I hit the stop button. What we'll do for that is to create a local variable, put it here, change it to read, and in there. Now we will have an additional error here, which says you can't have a latch option with the boolean. This means it automatically pops out. Pressing Ctrl E will get you the front panel. So here we have it. And we need to change this to mechanical switch when pressed. The problem with this is after you press it when it's running, it won't pop out again until you press it out again. So the next time you run it, it will just stop immediately. To counter this, we'll just make a simple thing here, change to right, and then set it as false. And to ensure that this starts before, or this is done before all the other one, we can use the error loop to control the sequence of events. So we have this one error, it goes in both of them. It's just an empty control. And we have it here. And then we can encapsulate this in a flat sequence structure. So using flat sequence structure is usually useless. Most of the time there's a better solution. I only use it for this, just to collect things into one loop that I want to stop immediately, or for very specific FPGA or timing issues. So what happens now is that the first thing the application does is to set the stop button to false, because these two loops wait for the input here and here to start, and this won't be done before everything in this loop is done. So now we've set up the stop button. The reason we don't just create local variable here is because this raw data only holds the last data sent to it, which means we could lose some data if these run asynchronously, which we want them to do, and is the whole point of having two separate loops most of the time. And this is why that's not an option. What we need to do is put it in some sort of communication storage where the top loop here can read it at its own pace, making them unsynchronized but without losing any data. To do this, we will use a user event. You will not find it in the synchronize here, but instead you will find everything in the dialog and user interface here. Go into event, and then we'll pin this one. So to create a user event, we need the create user event. And to generate, to send it, we need to send it here. So we send the data in here. And then we need to destroy the event. And to receive it, we need to do something else. We'll make a little bit more space here. We will need an event structure. We'll gather this around everything in our code. And now this is in the timeout structure. You can see that here, which means every time it times out, which will be never since we don't have any input here. So this is the wrong event, but we'll fix this later. And for this one to know what to get in, we will need to register the user events and then unregister them when the loop is done, in addition to the other elements. So now we've picked up everything from this menu, we will just close it. The data we want to send is the raw data. What we'll do is just to create a constant here, and we'll put it in here. And then we'll show the label. Visible label. We'll call this raw data, as we've done. It's important with the name because this is what the user event in here will be called later. We want to ensure that this starts before everything else, like we did with this one. And then place it in here. Let this wire go through this one so that we ensure that this thing starts before everything else. But the order in which these two happen doesn't matter because they're not dependent on each other. But we know that these things happen first before everything else, which is the important part. Let's start with the sending, as it's easier. We'll just remove this one here, and we will connect this one to the error wire. And then we can connect it here. So now this one knows that it will send raw data. So if I put in something like the millisecond here, we will see an error. But if I put in this waveform, there is no error. We then need it to go to the close. We'll put it here, this error in here, error here. We can also just make the error out now. So we'll just make an indicator here and call it error out acquisition. And we will also make an error out here. So we can see an error that goes here. Now when this runs, it will send the data every loop. But we still don't have a receiver. To set up the receiver, we connect this one to the event. We then connect this one into this register user event, and we want to connect it to the error loop. So we'll just move it here. Usually when you make new events, you want to add new event, but we want the content of this event to just work for another thing and not the timeout, which it says here. So we'll just click raw data. And then we need to connect up this one because this registers an event and then it's good to close it. It's not vital. I didn't use it in the beginning, but there's some uncertain errors which can occur if you don't do it, and uncertain errors is the worst to debug. Then we'll just hook it up to this one. Oh, we see this missing an input here, so we will go to the error loop. So now we have a way that this data is being sent here, from here to here, while both of them are running. The other advantage with this, when no user event is being sent, it's on standby, which means it doesn't overload the CPU or use too much RAM. It just waits, doing nothing. Okay, so now we have the data going here, being sent here, and to receive it, we need the raw data output here, and we connect it here. You can also rename this to raw data in. And now this one can receive the data in parallel with this one without interfering. So if this one just freezes up or has a hold for any reason, this will just push the data in here, and there will be created a queue, and the data will just be read as fast as this one can read. So we have a few errors left, as we can see with the broken play button. And this is probably just the wiring here. And now this should do the exact same thing as what we started with, but it will do it in parallel without anything interfering with the acquisition. This will make more sense when we make the larger application, when we add more and more here, things that would hold up the application, stopping this one from reading. So let's test it now. Control E, press play. We get nothing here because we haven't selected the amount of samples. Let's say 10. And here we get something. I won't hook up to read the pulse because it's the same one as last time, but what I will do is I'm tapping the input and we see it works exactly like the last time. And we can test this one too. Remove 5 seconds. And we see 10 minus 5 is 5 seconds. So this works too. That's it for lesson 3-1. We separated the hardware out and set up a communication between the loops, making it possible for them to run in parallel. We also set up a local variable here. We also set up a local variable here to stop both loops when you want one to stop. In the next lesson, we will separate out the graphical interface the buttons and indicators out from the processing